So we're covering chapter 2, limits and their properties. This is section 2.3. In this section, we're going to evaluate limit using different properties. So these are the objective for the section. We first start with the properties of limits, and then we talk about different strategy for finding the limits. And eventually, we're going to discuss about the Squeeze theorem for finding the limit one more time. If you have a function f of x and that function is defined at c, for example, let's say c is a point. Let's say you have a function look like this, and this function is defined at point x equals c. Then function like that might have a limit as a value of the function at c. That comes from direct substitution. So sometimes that's possible and sometimes not. But whenever it's possible, we can find the limit of the function when x approaches to c. Approaching means when the value of x goes very, very near to c from left side and right side. The limit of the function is supposed to be equal to the value of the function at that point. Okay? That's coming from direct substitution. There is one theorem 2.1, some basic limits. The first one says the limit of any constant function, let's say here the constant is b, the limit of any constant when x approaches to any number, we don't care about that c, would be always the same constant. Meaning, think about this. Let's say you have a constant function f of x equal 5. No matter where you would like to find the limit, let's say x equal 1 here. So when x approaches to 1 from the left side and right side, the value of the function is still would be same, that is 5, because the function is constant function. And number 2, it's a identity function. Whenever you have the function itself is x, then the limit of this function is just replace that x by c. And for the power function, just replace x by where you are trying to find the limit. Keep in mind, this power function only works if the power n is positive integer. So what is the limit of x give? When x approaches to 1, that x, you just have to replace that x by 1, and then that is actually 1. Okay? Some examples. The limit for the first one, because it's a constant function, that would be 3. Limit for the second one, because it's identity, you just replace x by -4. And limit for the third one, you just replace x equal 2 and you do the math here. Okay? More properties. Let's assume that there are two functions, f of x and g of x. And L and K are their respective limits when x approaches to c. These are the given facts. Okay? And also b and c are some real number, n is a positive integer. Then these are the three properties we can always apply. If you are looking for the limit of b times the function, you can keep this b outside of the limit. So that would be b times the limit of the inner function, which is L. You see here? So for example, let's say you would like to find out what is the limit of 5 times x. Then using this property, you can say, hey, this is the limit of this function is 5 times the limit of x itself, which is, if you replace x by 1, it's a 5. The second one and the third one, sum and difference, the limit of the sum is equal to sum of the limit, because L and K, they are individually limit of the first function and second function. And the difference of limit of the difference of the function is equal to difference of the limit. Okay, these are the more properties. 3 more: product, quotient, and power. If you are looking for limit of product of the function, it's actually product of the limit, and limit of the quotient is actually quotient of the limit. But keep in mind, this is a little bit tricky. The limit on the denominator has to be non-zero. If it's 0, then we cannot apply this rule. These are the properties we are talking here. We are not making anything up here. It's just the properties we have given. Finally, if you are looking for the limit of the function to the power n, then you can just find the limit of the function inside this power, which is L, and that will give you L to the power n. Let's do one problem. Here is the 4x squared plus 3. We can apply these properties. So first of all, we can apply the sum rule, and then after that scalar multiplication, and this is what we're going to get. You see here, I'm applying the limit for the first term and then second term. That gives me limit for the first term, limit for the second term, and because this 4 is a constant, so I can keep that constant outside. I can find limit of x squared when x approaches to 2 and limit of 3 when x approaches to 2. This is power function. I just need to replace this x by 2, and this is constant function. No matter what limit we are trying to find, this would be always 3. By doing this, our final limit for this function is 19. We can also look at this answer or this limit by using a graph of this function. So this is the graph of given function, and as you can see here, when x approaches to 2, the graph is approaching to 19. That's why the limit is 19. Okay, there is another rule that helps us to find the limit of polynomial function and a rational function. So let's say p is a polynomial function. Finding the limit for the polynomial function is very easy. Just substitute x equal this value c. Very easy. For the rational function, you can do the very same thing. Just put x equals c in the given function, but keep in mind the denominator value has to be non-zero. If it's zero, then function would be undefined. So one example, let's say this is the example we have given, and we would like to find out the limit. First of all, we need to check what happens when x approaches to 1 to this denominator. If this denominator becomes 0, then you cannot directly find the limit. But here in this case, when x is equal to 1, this denominator part is not 0. So finding the limit is very easy here. The denominator is not 0 when x equals 1. So apply theorem 2.3 to obtain the answer. So this is the theorem 2.3. If you have non-zero thing, just apply, just replace this x by c. And that's what we can do here. Eventually, by doing that, from here to here, I'm just replacing x by 1. And after simplification, the answer is 2. We can also use some, graphing tool like a graphing calculator, or just plot the graph of this function. And we can see that when x approaches to 1, the graph approaches to 2. That's why the, limit is 2. There is another theorem that's involve a radical. Radical means power, square root, a cube root type of thing. Here it's nth root. The limit of this radical sign is actually radical of the limit of inner function. But keep in mind that radical has to be even number. This n has to be even number. If you have, there is a restriction. This is true only if c is positive when n is even number. So what I'm trying to say is, if you have, let's say, square root of x, and if you are looking for limit of x equal when x approaches to 1 for this one, when x approaches to 1 for this one, so you see here is the even number. Even number means 2, because there is nothing, means it's n equal 2 here. And we can only apply this rule if x is, this value here is positive. If it's negative, then we cannot apply this rule. Okay, so that's the theorem 2.4. Theorem 2.5, it's a composition function. So for that, let's say you have limit of first function g of x is L, and second function when x approaches to L is f of L. If these are the two conditions we have given, then we can apply the limit for the composition of f and g. So we can bring this limit inside, and as you can see here, limit of g of x is L. So the limit of this composition function is the value of the function f at L. One example, let's say we're interested to find the limit of this. As you can see here, inside inner function, first of all, find out what happens to this inner function when x approaches to 3. That is, just replace this x by 3, and that will give you 8. And now we know when x approaches to 8, the the outer function, which is cube root of x, would be 2. So there are two ways you can find out. You can just find out the value of this function inside the radical sign, plug that value, and then do the simplification, which is cube root of 8 is 2. Okay, that's because of this is the composition function. Some more rules for limit of a trigonometric function. So as you can see here, c is a real number, and then limit of trigonometric function, for example, sine x, cosine x, tangent x, cotangent, secant, and cosecant, is just replacing the value of x by that limiting value sheet. So two more things. If you are interested to find the limit of a to the power x when x approaches to c, just replace this x by c. But that only works if a is positive. Second one, the limit of the natural logarithmic function is just replace that x by c. Some examples. The limit of tangent of x is when x approaches to 0, just replace x by 0. Limit of sine square of x when x approaches to 0 is again 0. Here we can use the product rule. We can find the limit for the first one, which is x, second one e to the power x, and eventually this is the answer we're going to get. And we can do the same thing here. So we're going to talk about some strategy for finding the limits. Okay, theorem 2.7, function that agree at all but one point. Let's assume that there are two functions f of x and g of x, and they are equal function except at one point c, and we would like to find out the limit of this function when x approaches to c. If they are equal everywhere else, then the limit of the first function and limit of the second function when x approaches to that point where they are not equal has to be same. That's the meaning of this theorem. I'm going to give you one example here. Let's assume that you have function x cubed minus 1 over x minus 1. So if you look at here, this function can be simplified. We can simplify this function and we can factor the top one as x minus 1 times x squared plus x plus 1. And we can cancel this x minus 1 on the top and x minus 1 on the bottom. And then that will give us x squared plus x plus 1. So here is the thing. We can, view them as a two different function where they are equal everywhere else except x at x equal to 1. So g of x, which is x squared plus x plus 1, let's assume that this is one function, and f of x is this one. So as you can see here, this function f of x is not defined when x equal to 1 because of this denominator. But this function g of x individually, this is defined everywhere else. But as you can see here, after simplification, f of x and g of x, they are same thing except at x equal to 1. So they are same function except at one point. So this is the graph for the first one. As you can see here, when x equal to 1, there is a hole, meaning this function is undefined at x equal to 1. And g of x doesn't have hole. It's defined everywhere else. And basically they are same function except at 1. So when we try to find the limit of this function when x approaches to 1 from the left or right, they have to have the same value. That's the meaning of this theorem we have given here, 2.7. So in this case, the limit is when x approaches to 1, the value of the function from g of x, as you can see here, it's a 3, which is the limit of the function. So they are same. Okay, that's why the limit is 3. Okay, so when finding the limits, we have to, we can use this strategy here. First of all, learn to recognize which limits can be evaluated by direct substitution. Because if you can do that, then that will be easier for finding the limit. And then after that, when the limit of f of x as x approaches c cannot be evaluated by direct substitution, then we have to simplify that whenever it's possible. So try to find a simplified form of that function. Like we did in previous example, we simplified the f of x and we got the g of x. Now by using the previous theorem, theorem 2.7, we can find the limit of that simplified form, and the limit of that simplified form would be equal to the limit of the original function. And then if it's possible, use a graph or table to find the conclusion. So these are the three tips we can use while finding the limits. So one of the technique we can always use is whenever it's possible is dividing out technique. So for example, let's say you have a function x squared plus x minus 6 on the top and x plus 3 on the bottom. When x approaches to -3, the bottom part approaches to 0. 0 on the denominator is undefined. So theorem 2.3 cannot be applied because the limit of the denominator is 0. You see here? It's actually 0 over 0. So for finding the limit of this type of function, we need to simplify. We need to find out the factors on the top. In this case, it's x plus 3 and x minus 2. And there is x plus 3 on the bottom. So we can cancel the same factor. And then leftover would be x minus 2. Now we can find the limit of this simplified form, which is when x approaches to 3, the value of this x minus 2 would be, just plug x equal -3 here, and that will give you -5. So the limit of this function, the original function, is the limit of this simplified function g of x when x approaches to -3, and then answer is -5. So by using theorem 2.7, they are same function except at one point where we are interested to find the limit. So the limit of the function for both of them, limit of both of this function when x approaches to -3 has to be same using the theorem 2.7. So that's why the limit is -5. So the idea is always try to simplify and find the limit for the simplified form. The graph for the simplified function is, as you can see here, this is the graph for the simplified function, which is as you can see here, x minus 2. So this is the graph for this is the graph for function f of x, which is very similar to the x minus 2. But this function is undefined at -3. So in previous example, as you can see here, when you try to find the limit on the top, which is 0, and limit on the bottom, which is 0, this type of form has a special name that's called indeterminate form. An expression such as 0 over 0, which we just discussed, is called an indeterminate form because the limit cannot be determined. When this form is encountered, whenever you see this type of form, always rewrite the fraction so that the new denominator does not have 0 as its limit. So whenever you have indeterminate form, try to simplify that form, and then we can find the limit. There is one technique called rationalizing technique. Sometime we might have to use this technique. For example, in this rational function on the top there is a square root. We cannot just find the limit of this function because when x approaches to 0, the denominator is 0. So it will be 0 on the top and 0 on the bottom, which is one of the indeterminate form. So we cannot find the limit as is. So we need to use this technique called rationalizing technique, which can be done by multiplying the top part, in this case, by its conjugate. Conjugate means all the terms are same, but the middle sign is changed. You can multiply the top part, and that depends where your radical sign is. If it's on the top, then you have to multiply by that, the conjugate of the top part. If this radical is on the bottom, in the original problem, then you have to multiply the conjugate of the bottom part. So in this case, the radical is on the top part, so we're multiplying on the top and bottom by its conjugate. After multiplication, this is what you are going to get. Just do the step-by-step multiplication. Okay, if you remember, if you multiply a plus b and a minus b, they are conjugate of each other. The multiplication would be a square minus b square. In our case, a is square root of x plus 1, so the square of square root is x plus 1. b is 1, so square of 1 is 1. So on the top part, you have x plus 1 minus 1. After cancellation, it would be x. On the bottom part, you have x times this conjugate terms. You can cancel this x on the top and this x on the bottom, And now finding the limit of this expression, original problem is finding the limit of this simplified form. When x approaches to 0, put x equal to 0 here, and that will give us the answer. When x is 0, it will be 1 over 1 plus 1, which is eventually half. So that's the rationalizing technique. There is one very important theorem called the skews theorem. Skews theorem means, let's assume that there are three functions: function g, function h, and f is in between them. Okay, so as you can see here, when x approaches to c from the left and from the right, the function g, the limit of the function g is this value. Limit of the function h is this value, the very same value. In that case, because of this squeezeness, because of this squeeze theorem, limit of this middle function f would be very same as the limit of upper function and the lower function. Okay, the limit of the function f of x when x approaches to c exists, and that is equal to the limit of the upper function and the lower function, which is same L. Okay, so let's assume, let's try to find out the limit of these three examples here. Limit of sine x over x is 1. Limit of 1 minus cosine x over x is 0. Limit of 1 plus x to the power 1 over x is e when x approaches to 0. These are actually the very special case of this skews theorem. You can find out, you can bound them, you know, upper bound and lower bound, and you can find it. These are very special case of this skews theorem. I'm not going over these three examples here, but they are a special theorem, theorem 2.9. So that's one of the rule. Okay, by using these rules, we can find out the limit of this type of function, tan x over x. There is no rule for tan x over x. So what we can do is we can split this tan x over x into sin x over x times 1 over cosine x. Now we can apply the limit for the first function, which is 1, limit for the second function, which is also 1, by applying that limit by using the product rule. So that's why the limit of 10x over x when x approaches to 0 is also 1. Okay,